Okay, good morning everyone. Thank you for being here. Today I want to show you the origin of the sedimentary field of Oligocene-Miocene age in the Levant Basin and its link to the major geodynamic events that shaped the Eastern Mediterranean. Overall, my PhD thesis consists of 5 chapters addressing geological questions across the Eastern Mediterranean, primarily from the perspective of siliciclastic sediment provenance. 2 of them in the Kyrenia terrain of northern Cyprus and along the Cyprian convergence zone address the tectonic evolution at the northern parts of the Eastern Mediterranean. 3 of them, focusing on the Levant Basin, will be presented today. The Eastern Mediterranean region, with the Levant Basin at its heart, has been highly geodynamically active over the past 34 million years. Much of its present-day topography, from Ethiopia in the south to Anatolia in the north, developed during this period, reaching a mean elevation of more than 500 meters. In the south and in the east, regional doming and uplift commenced in the late Eocene, driven by the rise of the Afar mantle plume that impinged on the base of the Afro-Arabian lithosphere. Uplift continued also during the Oligocene and intensified after Red Sea rifting was initiated in the late Oligocene. In the north, collision between the Arabian and Eurasian plates along the Bitlis-Zagros suture gave rise to the Bitlis-Zagros orogenic belt with intensified orogeny starting from the early Miocene. This geodynamic reorganization has significantly reshaped the drainage system, leading to the formation of major rivers such as the Nile, Euphrates, and Tigris, which drain the uplifted areas, transporting sediments across thousands of kilometers to the deep sea. The geodynamic evolution of the continental areas on both sides of the Eastern Mediterranean differs significantly and is well reflected in the regional geology. Among the most prominent features in the south are juvenile Neoproterozoic basement rocks that crop out around the Red Sea, and the thick sequence of Cenozoic age continental flood basalts that cover the Ethiopian plateau associated with the rise of the Afar mantle plume. In the north, abundant Upper Cretaceous ophiolites, magmatic and metamorphic rocks mark the imprint of convergence processes in the southern Neotethys. As a result of uplift in Northeast Africa, the Nile River system evolved, transporting sediments from the Ethiopian plateau to the Eastern Mediterranean. Recent geological evidence suggests that the Nile reached its present-day proportions already before 30 million years. It delivered an enormous volume of sediments during the Oligocene and Miocene, estimated at 400,000 cubic kilometers that were mainly deposited in the Nile cone but extended also into the Levant and Herodotus basins. Coeval with the Nile, a large fluvial system which no longer exists, evolved on the Arabian side of the Eastern Mediterranean, transporting sediments from inland Arabia to the Levant Basin through submarine canyons that incised the Levant continental margin. This system is responsible for the deposition of thick clastic units of Miocene age that are preserved along the Dead Sea Transform Valley. These are the Hatzeva and Ordus formations in Israel. However, the southward thickening of the Oligocene and Miocene isopachs within the Levant Basin towards the Nile Delta favored the Nile as the main sediment supplier to the Levant Basin, to the Eastern Mediterranean from its southern parts. The orogenic belt at the northern parts of the Eastern Mediterranean was drained westwards, also delivering a vast amount of siliciclastic sediments into the deep sea. These sediments were deposited in a series of basins along the southern Anatolian margin. An outstanding example for the large sediment influx into the northern parts of the Eastern Mediterranean comes from Cyprus, where a 2 kilometers thick section of Oligocene and Miocene deep water turbidites is exposed. These sediments may have reached also farther south into the Levant Basin. After years of debate regarding the age of the sedimentary field beneath the Messinian evaporites in the Levant Basin, with estimates ranging from the Cretaceous to the Miocene, recent commercial drilling provided proof that this section is of Oligocene and Miocene age or of Oligocene and Miocene age siliciclastic sediments. The siliciclastic section beneath the Messinian evaporites is primarily composed of shales with several distinct sandstone horizons, including lower Miocene sand intervals that host world-class hydrocarbon reservoirs. These are the Tamar sands. Until recently, direct investigation of the Oligocene and Miocene sediments in the Levant Basin was limited to a single study that applied chrono, chemo, and biostratigraphy to 2 borehole sections. However, the question of the provenance of the siliciclastic sediments and their link to the regional geodynamic events remained open and controversial, with 3 possible sources and 2 possible geodynamic associations. The first 2 sources, Northeast Africa and Arabia, are associated with regional mantle-induced uplift in Northeast Africa and Arabia, whereas the third source in Anatolia is associated with plate collision. The goals of this study were to determine the origin of the clastic field of Oligocene and Miocene age in the Levant Basin by direct investigation of the buried sediments, and to assess the link between siliciclastic sedimentation in the Levant Basin and the regional geodynamic events that shaped the Eastern Mediterranean. A source-to-sink approach underpins this study, where sink sediments, in this case the Levant Basin sediments, hold valuable information for deciphering their source, sedimentary pathways, and the entire geodynamic association. To achieve this, I've integrated several provenance techniques, including sandstone petrography, detrital zircon uranium lead hafnium isotopes, heavy mineral assemblages, clay fraction bulk and isotope geochemistry, and clay mineralogy. All in all, in this study, I aim to examine continental scale processes from the perspective of micrometer scale sediments. So let's dive in first with the provenance of the sand fraction of the siliciclastics. To decipher the provenance of the sand fraction and to reveal spatial and temporal provenance variations, I've sampled several stratigraphic intervals from 4 boreholes across the basin. These are from south to north, Mira, Dolphin, Leviathan, and Karish North. The sampled intervals, marked by white stars on these first-time published columnar sections, range from the lower Oligocene to the upper Miocene, approximately 32 to 7 million years. Among the most interesting features of the siliciclastic section in the Levant Basin are the lower Miocene Tamar sands interval, which again host large hydrocarbon reservoirs. These sandstones that were sampled from drill core and cuttings are very rich in quartz and contain a small proportion of other minerals. The Tamar sands intervals cover a large area within the basin of approximately 30,000 square kilometers with minimal thickness variations. Provenance evaluation of the sand fraction primarily relies on the composition of heavy mineral assemblages and the detrital zircon content. Out of the bulk sediment of each sample, I've separated the heavy mineral fraction, which contain various dense minerals such as zircon, tourmaline, rutile, and apatite. The heavy mineral fraction was then analyzed using the scanning electron microscope to determine the mineral abundance. Out of the heavy mineral fraction of each sample, I've separated 120 zircon grains by end picking under a binocular microscope. These zircons were then imaged using cathodoluminescence to reveal their internal structure. A suitable domain for further analysis was then chosen in each grain, and each of these spots was analyzed for uranium-lead geochronology. Finally, a zircon age relative probability diagram was plotted for each sample. The relative probability diagram shows the detrital zircon age distribution and reveal the prominent zircon age populations in the sediment. Here, for instance, neoproterozoic zircons predominates, forming 3 zircon age modes at 600, 750, and 950 million years. 600 million year zircons form the most prominent population and are the most abundant in this sediment. Other zircons, as old as 2.6 billion years, are found in smaller quantities in this sediment, forming 2 smaller age populations. Both the zircon age distribution and the heavy mineral assemblage are diagnostic of the sediment source. Identifying the particular source of the sediments using detrital zircon data has only recently become possible thanks to several studies that have characterized the detrital signal of the different sources around the Levant Basin. The Northeast African source is fingerprinted by Nile Delta sediments or by Nile Delta sands is characterized by a relatively small proportion of zircon grains older than 900 million years, as can be seen in this pie diagram, and a few Mesozoic and Cenozoic age zircons that sourced from the Ethiopian plateau. In contrast, the Arabian source, as fingerprinted by Hatzeva and Ordus formations in Israel, is characterized by a larger proportion of zircon grains older than 900 million years, approximately 45%, with no Mesozoic and Cenozoic zircon present. The older zircons form several zircon age populations on the relative probability diagram, which do not appear in Nile Delta sands. The Anatolian source in the northern parts of the eastern Mediterranean is distinguished by having a very large proportion of Mesozoic and Cenozoic zircons that reflect the regional geology at the northern eastern Mediterranean. In the Levant Basin, a single sandstone interval of lower Oligocene age from the base of Leviathan Boreal contain a large proportion of zircon grains older than 900 million years, with no Mesozoic and Cenozoic zircon present. It resembles Hatzeva formation sediments, indicating a dominant Arabian source. Upsection intervals of upper Oligocene and lowest Miocene age contain less zircons older than 900 million years, with some Mesozoic zircons present, indicating a dominant Northeast African source. Lower Miocene sand intervals, the main section of the Tamar sands, again contain a large proportion of zircon grains older than 900 million years, with no Cenozoic and Mesozoic zircons present, resembling Hatzeva formation sediments and indicating a dominant Arabian source once again. Intervals of middle to late Miocene age from all four boreals again resemble Nile Delta sediments and indicating a dominant Northeast African source for them. So here I found that the provenance of the sand fraction in the basin is uniform spatially, but varies temporally up the silicic-elastic section. The detrital signal of the Anatolian source was not recognized in the sand interval of the Levant Basin, indicating that sand did not reach the Levant Basin from the northern parts of the eastern Mediterranean. These correspondences are more easily seen through a multidimensional scaling analysis, where similarities in detrital zircon content are represented by sample proximity on this two-dimensional field. Lower Oligocene and lower Miocene sediments from the Levant Basin and the sediments of Hatzeva and Ordus formation in Israel clustered together, where upper Oligocene, lowest Miocene, and middle to upper Miocene sediments from the Levant Basin plot closer to Nile Delta units. Heavy mineral assemblages corroborate the interpretation obtained from the detrital zircon data. Lower Oligocene and lower Miocene sediments resemble and contain a large proportion of detrital apatite grains of sedimentary origin, akin to the Hatzeva formation. These grains were probably derived from erosion of phosphorite beds from around the basin. In contrast, upper Oligocene, lowest Miocene, and middle to upper Miocene sediments contain less apatite, but are enriched with amphibole and epidote in green and yellow color, indicating larger detrital contribution from igneous source rocks. The absence of chromite from the heavy mineral assemblages indicate that sand did not arrive the Levant Basin from the northern parts of the eastern Mediterranean, as chromite is a common mineral that derived from the erosion of ophiolites. In addition to the detrital zircon uranium-lead geochronology, I've measured the hafnium isotope signal in the detrital zircons. Zircons that plot, here you can see the detrital zircon uranium-lead ages versus their hafnium isotope composition. Zircon grains that plot above the true line, and particularly those who plot within the depleted mantle field, were derived from juvenile igneous rocks. In contrast, zircons who plot below the true line were derived from non-juvenile igneous rocks. The overall detrital zircon uranium-lead age and hafnium isotope pattern of the Levant Basin sediments resembled the pattern obtained from Paleozoic sandstones of Israel and Jordan, shaded here in gray. It indicates that the Levant Basin sands were derived from erosion and reworking of older sandstones of Paleozoic and perhaps Mesozoic age. They were not derived directly from erosion of juvenile Neoproterozoic basement rocks of the Arabian-Nubian Shield that crop out around the Red Sea. This observation is supported by sandstone petrography, which revealed the presence of secondary overgrowths on quartz grains that were rounded during transportation, indicating the recycling of previously cemented sandstone into the investigated sediment. So overall in this study, I've determined the source of the sand fraction of the silicic elastics by direct investigation for the first time. I showed that during the Oligocene and Miocene, sediments arrived at the basin from both Northeast Africa and Arabia, but in temporally varying proportions. The lower Miocene hydrocarbon-bearing Tamar sands primarily originated from the Arabian sources east of the Levant Basin. The quartz-rich sandstones were recycled from older sandstone units, and sand from the northern parts of the eastern Mediterranean did not reach the Levant Basin in the south. Up until here, I assessed the provenance of the sand fraction of the silicic elastics, but as sand intervals constitute just about a third of the entire silicic elastic section in the Levant Basin, it is crucial to understand the source of the shale fraction to gain a comprehensive view of the entire source-to-sink system. So where all these fine sediments arrived from? To evaluate the provenance of the fine sediments, I've sampled the clay fraction from 30 intervals from the different boreholes. The sample intervals, marked by these white hexagons, range from the lower Oligocene to the upper Miocene, including portions of the Messinian section. Clay fractions from the Levant Basin are composed of variable proportions of kaolinite, illite smectite, illite, and chlorite. The lower part of the sections are enriched with kaolinite in pink color, while the upper parts are enriched with illite smectite. There is an inverse correlation between kaolinite and illite smectite up the silicic elastic section, which I will address later in this talk. However, the absence of a large proportion of chlorite, talc, and serpentine, common minerals that derive from the erosion of ophiolites, again negates the detrital contribution from the northern parts of the eastern Mediterranean, as was also indicated by sandstone provenance. Here, the strontium-neodymium isotope composition of the Levant Basin sediments is plotted against the strontium-neodymium fields of various possible source rocks in Northeast Africa and Arabia. These include the Cenozoic continental fluid basalts of the Ethiopian plateau, Neoproterozoic basement rocks of the Arabian-Nubian Shield, and older silicic elastic sediments represented by the Paleozoic sandstones of Israel. Samples from the Levant Basin generally stretch between two end members, the Cenozoic continental fluid basalts and the older silicic elastic sediments. However, most of them plot within the strontium-neodymium field of the Neoproterozoic basement rocks of the Arabian-Nubian Shield, similar to recent sediments that derive directly from these rocks in red, and very distinct from sediments that derive directly from erosion of Cenozoic continental fluid basalt in green. It implies that the clay fractions from the Levant Basin were mainly derived from erosion of juvenile Neoproterozoic basement rocks that crop out around the Red Sea. To determine the specific source of these sediments, I compared the strontium-neodymium signals to those of coeval sediments in the Nile Delta in blue, which fingerprint the Northeast African source, and Hatzeva Formation in yellow that fingerprint the Arabian source. The dominant provenance of the sediments generally changes with time and follows the trend marked by this brown line. Oligocene and lowest Miocene sediments from the Levant Basin plot here. They resemble Nile Delta sediments, indicating a dominant Northeast African provenance. Up section, sediments of lower Miocene age show a larger detrital contribution from the Arabian sources. Middle to upper Miocene sediments, again, are more similar to Nile Delta sediments, indicating a dominant Northeast African source once again. So overall, I found that most of the clay fractions were sourced from Northeast Africa via the Nile Delta, with significant detrital contribution from the Arabian sources in the early Miocene. To summarize the provenance of the entire siliciclastic section, also including its sand-rich parts, the left panel shows variation in the neodymium isotope signal up the borehole sections in the Levant Basin. The panels to the right shows variations in the detrital constituents that were used to distinguish between the different sources in the sand fraction. This includes the proportion of zircon grains older than 900 million years, the proportion of apatite grains in the heavy mineral fraction, and the presence of Mesozoic and Cenozoic age zircons marked by these zircon-like shapes, which are again sourced from the Ethiopian plateau. Dashed lines in blue and brown show the average values of Nile Delta and Haseba Formation sediments. Both in clay and in sand, mixing between the two sources is evident. However, the Nile signal controls most of the record. Significant detrital contribution from the Arabian sources is observed both in clay and sand in the early Miocene, with values shifting towards the values of Haseba Formation sediments. So overall, I found that although the Levant Basin was fed from Northeast Africa and Arabia simultaneously, the Northeast African source is mainly responsible for filling the Levant Basin with voluminous siliciclastic material. Significant detrital contribution from the Arabian source occurred in the early Miocene when the Tamar sands were deposited. So in this study, I showed that although sand was reworked from older sandstone units, the clay-sized sediments were mainly derived from juvenile Neoproterozoic basement rocks. Most of the siliciclastic section sourced from Northeast Africa via the Nile Delta. However, transport of sand and clay from Arabia peaked in the early Miocene. Lastly, sediments did not reach the Levant Basin from the northern parts of the Eastern Mediterranean, and the Arabia-Eurasia collision is not recorded in the siliciclastic section of the Levant Basin. To conclude this part, I'd like to link the deposition of the siliciclastic section in the Levant Basin to the geodynamics of Afro-Arabia. The left panel shows a compilation of thermochronology data from around the Red Sea, mainly apatite fission tracks and uranium, thorium, helium ages, that signify rock exhumation during uplift of this region. In blue, data from the African margin of the Red Sea, and in yellow, data from the Arabian margin of the Red Sea. To the right in red, calcite uranium-lead ages from faults along the Dead Sea transform that signify its onset in the late early Miocene. Here is a summary of sedimentary data from the Levant Basin. So the dashed line shows the cumulative thickness of the sedimentary section, whereas the solid line shows sedimentation rates. This is a summary of the provenance data that I acquired. Blue symbols denote dominant Northeast African provenance, and yellow symbols denote dominant Arabian provenance. During the late Eocene, regional uplift in Northeast Africa and Arabia begins. At that time in the Levant Basin, marl deposition began, indicating the initial entry of clastic material into the basin. During the early Oligocene, the Nile River system and Haseba fluvial system evolved, transporting sediments into the Levant Basin. At that point in time, the siliciclastic section in the Levant Basin started accumulating first under moderate sedimentation rates. In the late Oligocene, the Red Sea Rift was initiated, and immediately after, rift flanks were significantly uplifted, as can be deduced from the thermochronology data. Consequently, in the Levant Basin, sedimentation rates peaked, and sediment transport from Arabia reached its maximum. Quartz-rich sand from Arabia entered the basin through submarine canyons that incise the Levant continental margin, eventually blanketing the entire basin. In the late early Miocene, the Dead Sea transform was initiated, as can be deduced from the calcite uranium-lead ages. The evolving Dead Sea transform valley partially captured and bisected the Arabian sediment transport system, effectively cutting off sand supply from Arabia to the Levant Basin. An excellent shale seal was then imposed on the Tamar sands. Ever since, the Nile is the dominant sediment supplier to the Levant Basin. These figures show the entire source-to-sink configuration of the Eastern Mediterranean during the Oligocene and Miocene. During the Oligocene, regional uplift initiated new sediment transport system that conveyed sediments simultaneously into the Levant Basin. Meanwhile, in the north, sediments from the Arabia-Eurasia collision belt were also transported into the deep sea, but they did not reach farther south into the Levant Basin. In the early Miocene, after the Red Sea Rift was initiated, rift flanks were significantly uplifted. Intense erosion of sandstones along the Arabian margin of the Red Sea is responsible for the position of the Tamar sands in the Levant Basin. During the middle to late Miocene, the Dead Sea Transform Valley evolved as a significant morphotectonic depression that partially captured and bisected the Arabian sediment transport system. Nile sediments were, however, persistently transported into the Levant Basin. In the north, sediments were also conveyed into the deep sea, but they did not reach further south into the Levant Basin also during this period. And to the last part of this talk. So sediments are more than just passive recorders of their journey. They also hold clues about the landscapes they came from. Beyond revealing their provenance and geodynamic association, they can tell us about the climate, weathering processes, and erosional regime at the source area. So what else these sediments from the Levant Basin can tell us? As I showed before, there is an inverse correlation between kaolinite and elite smectite up the siliciclastic section in the Levant Basin. The lower parts are enriched with kaolinite and the upper parts with elite smectite. This trend is supported by clay fraction bulk geochemistry, which shows that the lower parts are enriched with alumina and the upper parts with calcium and sodium. The notion that the fine sediments from the Levant Basin were mainly derived from erosion of Neoproterozoic basement rocks of the Arabian-Nubian Shield is supported by clay fraction bulk geochemistry, which also shows that the fine sediments from the Levant Basin resembles recent sediments that derive from these rocks and are very distinct from sediments that derive directly from erosion of continental flood basalts. The central panel shows the ratio between kaolinite, elite smectite, and kaolinite in the different borehole sections in the Levant Basin. The panel to the right shows the ratio between calcium and sodium and alumina up the borehole sections. Low values signify the dominance of kaolinite, and high values indicate the dominance of elite smectite. The left panel shows variations in the chemical index of alteration, which measures the degree of chemical weathering of the source rocks. So high values indicate intense chemical weathering. Kaolinite, the dominant mineral in the lower part of the section, is the main carrier of alumina in laterites, layers that form by intense chemical weathering. Laterites had formed extensively over the African continent from the late Cretaceous to the late Eocene under warm and wet climate and tectonic quiescence. The distribution of these laterites is presented on this map in orange color, including around the Red Sea, the source area for the sediments in the Levant Basin. In contrast, elite smectite reflects erosion of pristine rocks or initial weathering and erosion of pristine rocks. Such laterites are mostly preserved today in Ethiopia and Eritrea, where a thick cover of continental flood basalts protects them from erosion. Elsewhere in Afro-Arabia, they were largely eroded and are found today in isolated patches. Assuming that the siliciclastic section in the Levant Basin inversely mirrors the rock column that was eroded from the source area, it implies that it was composed of laterites and perhaps saprolites that developed from Neoproterozoic basement. Erosion first supplied the basin with kaolinite-rich material, and as it progressed, it gradually supplied more and more illite-smectite-rich sediments. With this simple observation, I'd like to describe the topographic evolution of Afro-Arabia during the Oligocene and Miocene. So from the late Cretaceous to the late Eocene, laterites formed under warm and wet climate and tectonic quiescence. During the late Oligocene and early Miocene, regional uplift began, driven by the rise of the Afar mantle plume. The laterite layers that covered large area around the Red Sea started to peeling off, and kaolinite-rich material started moving into the Levant Basin. As uplift continued, and particularly after the early Miocene, when rift flanks were significantly uplifted, fluvial incision intensified, cutting into the pristine bedrock. Elite smectite-rich sediments were then transported into the Levant Basin, settling on top. To wrap it up, I'd like to link the sedimentary record from the Levant Basin to environmental conditions and topographic evolution. During the Paleocene and Eocene, laterites widely formed under warm and wet climate as indicated by the marine oxygen isotope record. In the late Eocene, when the Afar plume rise, regional uplift began and clastic material started moving into the Levant Basin. The age of the oldest kaolinite-rich sediment in the Levant Basin, as shown by the mineralogical and geochemical indicators, is approximately 32 million years, providing a minimum age constraint for the onset of mantle-induced uplift and the peeling off of the laterite layers. By 20 to 15 million years, elite smectite becomes the dominant mineral in the basin, reflecting significant fluvial incision into the pristine bedrock and the establishment of rugged topography around the Red Sea. This aligns well with thermochronology and topographic reconstructions from around the Red Sea, which shows nearly the same picture. Apatite fission tracks in black and apatite uranium-thorium ages in gray shows increasing but still moderate rock exhumation during early stages of uplift in the late Eocene and Oligocene. Rock exhumation accelerated in the early Miocene when the Red Sea rift flanks were uplifted. Topographic reconstructions revealed that the Ethiopian plateau was already uplifted in the early Oligocene. However, uplift north of the Ethiopian plateau progressed gradually, reaching the elevation of about 1 kilometer only in the late early Miocene. This is in line with my findings that indicate early stage uplift at 32 million years and the establishment of topography already before 15 million years. So the Levant Basin of the Eastern Mediterranean acts as a natural sedimentary sampler of the vast area in Afro-Arabia that was uplifted, providing a unique perspective on its uplift process. It offers independent sedimentary constraints on the uplift history of this region, 32 million years for the onset of uplift, and 20 to 15 million years for the establishment of topography around the Red Sea. Lastly, clay mineralogy and geochemistry provide a tool for reconstructing the uplift history of geodynamically active regions. Finally, I'd like to acknowledge my many teachers and students from whom I learned the most, my supervisors, Dov and Avot, for accompanying me along the way, many colleagues, collaborators, friends, and people who helped me to conduct this research, my beloved family, Noah and Eleanor, who are very much familiar with what I've just presented and have made every obstacle feel manageable with a smile, my advisory committee, Zohar and Olga, the administrative staff here at the Institute of Earth Sciences, and of course the Israel Ministry of Energy for supporting this study, and the various companies that provided the valuable borehole material. And with that, I'd like to conclude, and thank you all for listening.
Questions?
Right. Very cool talk. So I wonder if you can comment on
here assumes that minerals come from different sources and are recorded as is in the scene. Can you make a comment on what can happen and how can this analysis change if you consider weathering during transport and maybe diagenesis? This is the second thing. Fertility biases and maybe sediment routing. I mean, you mentioned that it's all, you have turbidites that transport sediment, route sediment in the basin. Can this affect the composition of, let's say, clay minerals?
So to overcome this thing, I've analyzed sand and clay separately. I didn't analyze the silt fraction, which mixed them both, the detrital grains and clay. But elite smectite don't form usually don't form directly from the erosion of igneous rocks. Smectite forms, and I assume that during diagenesis, elite smectite was formed. However, this is randomly interstratified elite smectite, so elitization processes were limited.
You mean elitization
during burial and diagenesis? Yes.
Yeah.
That's it, I think.
Yes, so, but regarding, for instance, fertility biases for the zircon assemblages.
Yeah,
So
there is some fertility biases, of course, because I've analyzed only the fraction that is coarser than 63 microns. Okay, I could have analyzed smaller grains, but the fertility of zircon grains is could be achieved in this fraction better. There's also the limitation of the analysis. The laser spots are 30 microns, so we can't go too small.
Just to be clear, I'm referring to, let's say you have different terrains contributing zircons.
Yeah.
Some of them are richer in zircons.
You mean the...
Can bias the distribution, right?
Yeah.
So, and I think you showed some numbers, right? Like the percentage from the heavy minerals assemblages, right? Of zircons for two sources.
Oh, I showed the proportion of zircon grains older than 900 million years.
Yeah. Well,
yeah.
Okay. Yeah.
Okay. So these zircons. I start with it. Here you can see a small amount of these zircons. It is because these sediments were largely derived from Neoproterozoic basement rocks of the Arabian-Nubian Shield. These sediments were derived from older silicic-clastic sediments that contain these zircons.
Right.
So we see difference in the detrital signal of both sources. So the Arabian source primarily delivered older sediments, like reworked sediments, and the Northeast African source delivered or supplied more contribution from igneous rocks, directly from erosion of igneous rocks. As I sampled the Nile Delta and Hatzeva Formation sediments, which I assume to fingerprint the two sources, I actually overcome this, because I know the detrital signal of both sources.
Adar, can you go back to the last slide of the elite smectite? So I think that there is another player on this table, and the other player is the Sahara Desert, because we know that at least, let's say, there are different estimates when the Sahara Desert was formed, let's say 10 million years. So from 10 million years, we start to get fine material from the Sahara Desert, and actually the main area of accumulation of materials that come from the Sahara Desert is the Nile Valley. So the Nile Valley can transport sediments for sure. It's the main carrier of sediments to this Mediterranean. But the question is from where the sediments arrive to the Nile Valley. And from 10 million years on, most of the fine-grained material arrived from the Sahara Desert is deposited in the Nile Valley, especially in this big area of the swamps between Egypt and Sudan. And the inlet smectite, and we know it, Amir can tell you more than me about it. You know, the inlet smectite are products of certain dust that come from the Sahara Desert.
Today.
Yeah, not only today. If you go to the Bira and Gesher formation, you see that at least from 9 million years on, and they come from the Sahara Desert. The Sahara Desert strontium and neodymium isotope signal is, however, different from the signal of... No, actually not. And this is another point. Because you showed on your neodymium diagram that most of the material, you know, it comes from the Arabian, let's say, from the Arabian plate. However, you had very negative numbers that are reaching something like -13 or something like this, right?
Yeah.
They should come, they don't have a source in the Arabian desert.
So this specific sample comes from a core sample of the Tamar sands intervals, and it plots down here. It's the only sample.
It's trending. The trend is going towards this composition.
Yeah, of course. If you mix older siliciclastic sediments with more juvenile sources, you get that line. But here you can see mixing between older siliciclastic sediments and more juvenile sediments.
Right, but these sources that are trending towards very negative number of epsilon neodymium, they should come from the Sahara Desert. Because only there you have sources with very negative epsilon neodymium numbers.
But if you measure the strontium neodymium isotope signal of clay from Paleozoic sandstones, that's the field you get.
It doesn't stand in conflict. It could come there.
It could also come from there.
Right.
Yeah, that's true.
Anyway, I think that this should be considered. It doesn't change your interpretation, and just doesn't change the relationship to the geodynamic interpretation, which is very important. Because overall, the Nile River is the main carrier. The question is how, from where the sediments arrive to the Nile River.
To the Nile River, yeah.
Can you quantify, maybe you did in a research, can you quantify the actual fractions that came from African and Arabian sources at different times?
No, actually, it's quite hard to do it because I could use a simple mixing trend between this and this, yeah. But there are also different source rocks that contribute in different times. If I do the simple mixing line, I get like 60% from the Arabian source during the early Miocene.
That's the sand.
In the sand. Yeah, in the clay. Also in the clay, yeah. Also in the clay. And yeah, so 60% from the Arabian source in the early Miocene.
Thanks.
More questions?
You assume that the central in the basin is recycled Mesozoic and Paleozoic material. But the clays are not. Where are the clays of the recycled sandstone?
So I think that clay forms a very small proportion of this quartz-rich sand. And you can see here that the strontium neodymium signal during the deposition of the Tamar sands also shifts towards the signal of these Paleozoic sandstones. So you do see contribution from the clay fraction of the sandstones, but it remained subordinate with respect to the sand. So here you can see sediments, these 2 points, of Nile tributaries that drain Mesozoic sandstones and ANS basement. basement of the Arabian-Nubian Shield. Okay, it's a mixing between the two source rocks, and they fall here. Okay.
More questions? If not, I think we have cookies in almost
60 seconds.
in 60 seconds.
He's practicing it for 1
Yes.
month.
Yeah. So you're all welcome to the almost weekend gathering. Thank you.